So when we get a multi-step problem, we have two ratios that we want to set up. One of them can come from the equation, and we can predict delta H's using formation values. It's the most recent skill you just learned. Okay? You have delta H in an equation. You have moles in an equation. You might be given the delta H. Okay? You might have a multi-step question that's fairly fast because you're given it. Okay? Or you might have to predict it from molar enthalpies of formation. I'll make that a little bigger. So this is delta HMF. Products minus reactants, moles times molar enthalpy. Okay, so that's the equation. And then we might have another circumstance that we have to solve for. If we can get the delta H over N for the equation, we can solve for the delta H for a different amount of moles. Okay, this might be our question, or it might be a lab experimental situation. There are two delta H's because one is the equation, one is a lab situation. There's a moles in an equation, and there's moles in our lab or real life situation. Now we can take more steps, more multiple steps. The delta H, where we learned at the beginning of the unit to solve for that, would be MC delta T. Okay, and we can kind of go in and out, back and forth from MC delta T in a lab situation to delta H in the lab situation. Okay. If we knew the delta H in the equation and the moles in the equation, and then we were told we burned 10 grams, okay, you could solve for delta H. Okay. We did that recently, but we could keep going. Okay. If we knew how much energy was released, and I told you it went into 1 liter of water, so 1,000 grams of water, and we know the C of water, we could solve for the delta T. So that's one type of question. Could be asked, what's the temperature change when you burn 10 grams of methane? You'd need an equation for methane. You'd get how many moles of methane, get delta H, keep going, and solve for delta T. Okay. Or you could be given all the MC delta T data. You burn 10 grams of methane. The temperature goes up 25 degrees Celsius. It's 125 grams of water. So you can solve all the blue. The moles would give you the N. You can know the lab delta H and N, and you could use that to solve for the delta H in an equation because the moles will be in the equation. You can basically start or finish at any of the variables except for probably this one, because that's moles in an equation. You're not going to solve for moles in an equation, but everything else could be the answer or could be what you're trying to solve for. Okay. So we're going to do 2 examples. We're going to see one where we solve for delta H in an equation, and the second one I'm going to solve for this delta T. So you're going to see me go step by step, kind of all the way through this whole pathway, all the blue, the red arrow, into the green. So let's get started with the first one. Okay. Okay. Determine the experimental enthalpy change of reaction. So we're asked to figure out this delta H, but we're told use the experimental data. Don't predict it. Use the data in this question. So we're going to have to get the experimental enthalpy change, the experimental moles, and then relate it to the 1 mole that's in the equation. So I need to set up how we're going to solve for this experimental delta H. Using our typical layout or strategy that's going to let us solve most of these, delta H over N for an equation, is going to equal delta H over N for a question or a lab circumstance. We're actually after, for the first time that you've seen it from me, we're after the enthalpy change for the equation. Okay. Every other time we're after the delta H on the right-hand side. So let's try to connect. So that delta H that I put a red star is that delta H for the equation. The moles in the equation, let's see what chemical. We got to keep reading and see what chemical we're talking about. Okay. For the reaction, when 35.2 grams of chloride So the question talks about chlorine gas, so we're going to keep using the moles of chlorine all through this question. So there's 1 mole of chlorine. Okay. How much experimental energy was released? We don't even have to do MC delta T. The energy released was calculated for us. We have the heat was 42.1 kilojoules. Okay. The moles that cause that is this 35.2. So I'm going to start putting those numbers into that relationship. So the change in enthalpy for the equation, we don't know. The moles, and we have to stick to chlorine in the equation, is 1 mole. Equals, now we're on the experimental side, the energy released was 42.1 kilojoules. It said released, so it's exothermic negative, and I have to divide that by how many moles experimentally caused that, and we've got that typical mass to moles conversion. We've got to get moles of chlorine gas. Moles is mass divided by molar mass. 35.2 grams divided by diatomic chlorine, so 2 chlorines. Atoms are 70.90. So 0.497 moles. Again, you'd keep all the digits in your calculator. Okay. So we've got 2 ratios not fully finished. About half a mole of chlorine ended up releasing 42 kilojoules. We want to know in the equation, which is 1 mole, how much energy would be released. If we kind of look at this and think through it a little bit, 0.495 is pretty close to a half. Half a mole releases a little more than 40. A mole is double half. The equation has double the moles compared to the experiment, so we should see about double the energy when we rearrange this. We should see 80-some kilojoules in the equation. Now, I'm not going to show all my work. I'm just going to rearrange this. When you solve for delta H, I'm going to kind of keep this red star through it to keep reminding you that's the equation delta H. We're going to get that. I really just had to bring that 1 mole to the other side, which will cause the mole units to cancel. We're just going to get how many kilojoules are released in our equation. Now, sig fig wise, there was 3 in the mass, so 3 in my bottom moles. There were 3 in the energy, and this 1 mole is exact. That's a stoichiometric coefficient. So there's perfection, exactly 1 mole released. Okay, it's a whole number, the same way that count of students in this room is also a whole number. Okay, there's, I don't know, 20 some, let's say there's 25, that's not 2 sig figs, that's exactly 25 infinite sig figs. So I'm going to record this to 3 sig figs minus 84.8 kilojoules. So I use the experimental data ratio to solve for the equation enthalpy change. So our equation enthalpy change is 84.8 kilojoules for our 1 mole of chlorine. So this is my second multi-step. These are about this is as hard as it's going to get in chemistry 30. You'd only ever have one question on a test or diploma that's probably going to have this many steps. So we have 2.5 grams of zinc metal reacts with over 250 mils of hydrochloric acid. And we're asked what the temperature change of the solution would be. And then we're given a bit of information. We're told the molar enthalpy of reaction for hydrochloric acid is a little under 80 kilojoules per mole. We're getting that information so that we can write an equation with an energy, so we can get that first ratio, so that we can solve for the second ratio, but we got to keep going into MC delta T. So that's what I'll do when we're all set. So I'm going to set this up. I'm not going to balance that equation yet till we see the plan and the journey we're about to do. The reason we were going to need the equation and use that molar number is with that molar number, we could get the delta H for the equation. And we're going to balance this equation so we'll know the moles from the equation. The black are going to be known. So there are things we can figure out. We're going to do those right away. Okay. We've got a question, which is kind of a lab, real life situation. Okay. 2.5 grams of zinc in the lab was put into 252 mils of hydrochloric acid. You do that in the lab. Okay. So all the lab info I'm going to keep blue. We're going to need to figure out the lab delta H for the lab moles, which we're going to get. The lab moles is going to come from how many moles of zinc that we have. But this question isn't just delta H. We're going to have to get that blue delta H and keep going, because we need to solve for delta T. Once we know how much energy is released, the mass of where the heat went, so it looks like it's going into solution, and the solution would have to come from our only aqueous solution. So that 252 mils of hydrochloric acid would give us 252 grams of water. So that's where we're going to get our mass from. The C, we're just going to look up the C of water, and we can solve for that delta T once we know that blue delta H. So this is our journey. It's going to take me a few lines, deal with the black, deal with the blue, then we'll deal with the red. Okay? Now, if you're really strong at math and really good with algebra, you could do this. I'm not to, I'm going to break it down, but you could put MC delta T sort of right in for delta H, rearrange the whole thing for delta T and solve it. Okay? But that is not, I'm going to do it much more sequentially. Okay. So let's get started with the block. We need all the equation written out. So we're told zinc, which would be elemental zinc, reacted with hydrochloric acid. This is going to be a single replacement. The zinc is going to pair up with the chlorine. The zinc, which would be a cation when it's involved in the single replacement, we'll want to get the chloride, which will be our anion. Now zinc is 2+, chloride is minus, so that doesn't balance. We're going to need 2 chloride ions to balance that formula unit. And page 6 in the Alberta data booklets would predict that's aqueous. Hydrogen gets spit out in this single replacement, and hydrogen by itself is diatomic. Okay. That is not balanced. We have 2 chlorine at the end, so we need 2 chlorine atoms at the beginning. And now we have a balanced equation. We need the enthalpy change for this equation. That's why we're given this molar piece. Okay. If we weren't given it, we'd have to try to predict it using our data table. Okay. But we know the molar enthalpy of reaction for hydrochloric acid is this release of 76.5 kilojoules for every mole. Now, how many units of hydrochloric acid do we have in our equation? We've got a red 2. We've got 2 moles of this. The first mole is going to release 76.5. The second mole will release another 76.5. So the enthalpy change here is coming from the molar enthalpy, which we know, times the moles, the molar enthalpy times the 2 moles in our equation. Okay. We're doing all of this work in a multi-step problem, and all we've done is set up that black ratio. Okay. But we have the pieces we need. There's our delta H. Okay. And we'll have to think about what moles we're going to want. We're going to want the moles of the limiting reagent for this reaction. And that's going to be our zinc. We're not even told the concentration of hydrochloric acid. We know the volume. We don't know how many moles of this is. I'm going to assume that this is my limiting reagent. Okay. So now I'm going to work my way to that blue delta H. So delta H in the equation, minus 153 kilojoules, divide by, again, it's zinc is going to be our limiting reagent. So I want moles of zinc for both of my black and blue ends. Black N is moles in the equation. That's 1. Delta H, the energy released in the experiment, we're not sure. But we know there's 2.5 grams of zinc that cause that blue delta H, so we can get moles. Moles of zinc, mass, divide by molar mass, 2.5 grams, divide by, there's just 1 zinc in elemental zinc. Its atomic mass is 65.41 grams per mole. So we have 0.03822. Again, I'm not going to round down to 2 sig figs. I'm going to leave all of these in my calculator and write a couple extra on the board, or on a quiz, you'd write a digit or 2 extra. So the equation released this 153 kilojoules for 1 mole. We have way less than 1 mole, so we're going to have way less than 153 kilojoules. Let's figure out exactly how much. That blue delta H for our 2.5 grams. minus 153 kilojoules for 1 mole times our blue moles is going to go to the other side in the top when I try to get that blue delta H by itself. So our energy released is not even 6 kilojoules, 5.848 something kilojoules. I've rounded on the board, but not on my calculator. So this is as far as we went in previous examples, but we're going to turn that energy into a temperature change. So we're almost done. We dealt with the black. We figured out the blue. We now know this blue delta H. We know the mass of water. It's coming from the 252 mils of our acid. We know C. We're going to rearrange for delta T. So delta T, that blue experimental one, is equal to MC delta T, except it's really the absolute value. Delta T has a sign to it, MC delta T doesn't. So I'm going to just sort of drop that sign. Okay? I'm not going to bother putting the absolute value sign in. So the value, actually I'm going to rearrange this first. I always find it easier to rearrange the formulas without the numbers and then plug the numbers in. Delta T equals, so I want this by itself. The blue delta H is on the other side. That's good. The M, I have to move it over, so I have to divide both sides by M. The specific heat capacity, I need to move it to the other side, so I'm going to divide both sides by little c. And we're almost done. That delta T is our goal. Now I'm actually going to put this specific heat capacity value in first. This is aqueous solution. Water solution is the acid. So C is 4.19 joules per gram per degree Celsius. I like to put that in because it reminds me of the units I have to match all the way through. My mass must be in grams. 252 mils of solution, that is pretty much all water, will be 252 grams. A mil of water is a gram of water. Delta H I need to put in. This is where I have to watch. Delta H right now is in kilojoules, but my C is in joules. So a lot of students, if you find you get an answer and you're off by 1,000 times when you check the solution, go back to your work and look for like a joule kilojoules mix match. So I want this in joules so I can cancel down here. So this is 5.85 kilojoules, 5.85 thousand joules. I have 5,850 joules. Okay, so I did a conversion there, which is a multiply by 1,000 to get from kilo and get rid of it and go down to joules. So now my joules cancels my joules, my grams cancel my grams, and I have degrees Celsius on the bottom of the bottom. It's kind of like degrees Celsius to the -1 to the -1 again. 2 -1 powers would cancel each other out. Okay. The units, those degrees Celsius, end up being simplified to being on the top. I'm finally at the end, so I'm going to round. You know, it's good to peek at how many sig figs should you have. And 2 sig figs is the lowest we had in any of our information. So I'm going to put 2 measured digits. So it ends up being 5, and then I'm going to round it to 0.5. And that gives me my 2 sig figs. So that 2.5 grams of zinc put into about 1/4 liter of hydrochloric acid is only going to heat it up a little over 5 degrees. Okay. So I did, yeah, totally. I dropped this negative. We have to remember the negative means heat came out. So when heat comes out, we have to think of which way would the temperature go? Would it go up or down? So this is exothermic, heat is coming out, so things should get hotter. So this delta T we just solved for is how much the temperature would go up. So if the question said the temperature started at 20, it's going to go up to 25.5. Okay? If we had a positive value, positive delta H, it means it would have dropped 5.5 and would have to take that off the initial temperature. Okay? I have seen diploma questions where you have to get the delta T and then compare it to an initial. Okay? Again, this is probably longer than you'd ever see on a diploma. It's got a lot of steps. It would be a lot faster if this black line, the equation was just given to you, and then you'd save a step, and that might be on a diploma. Okay? Then you're just jumping into this step and the solving for delta T, and that's something you can maybe do in 3 to 5 minutes. Okay? So that's your second multi-step example. The first one was meant to be a little simpler, very common. The second one, as tough as it gets, less common, but certainly is going to be on either quizzes, a test, or that provincial exam.